Good evening, everybody. Today I am going to discuss about resonance in AC circuits. So, coming to outline, resonance in series RLC circuit, quality factor, bandwidth and bandwidth and half power frequencies. Okay, today we will discuss about series RLC circuit. I mean resonance in series RLC circuit. Tomorrow we will go for resonance in parallel RLC circuit. Okay. In today's lecture, we are going to discuss about resonance in series RLC circuit, quality factor, bandwidth, and half power frequencies. Okay. Yeah. Phenomenon of resonance in various domains. Okay. So here, this is wine glass. Wine glass. Okay. So if you produce sound waves near to this wine glass, okay, it vibrates. This glass vibrates. Okay. At one particular frequency, this glass breaks because of resonance. Because of resonance means every object has its own frequency. Every object has its own frequency. That frequency is called natural frequency of that particular object. Okay. Every object has its own frequency. That frequency is called natural frequency. Okay. So this glass is also having natural frequency. This glass is also having natural frequency. Okay. So if you produce sound waves near to this glass, okay, this glass starts vibrating. This glass starts vibrating. Okay. So at one particular frequency, this glass breaks. Means the frequency of waves produced by you matches the frequency of glass, then resonance occurs. Then resonance occurs. It is if the frequency of an object matches the frequency of the driving force. Okay. Here you are producing sound waves means it is having these sound waves are having frequency. Okay, it is having frequency, right? Okay, this frequency matches the frequency of an object, then resonance occurs. Resonance occurs means at resonance this glass vibrates with more amplitude. When the glass is vibrating with more amplitude means that may break. Okay, you may break that glass. You may break that glass by vibrating glass with more amplitude. Okay, so if you produce sound waves near to this glass, okay, if frequency of an object matches the frequency of sound waves produced by you, then resonance occurs. At resonance, this glass vibrates. This glass vibrates with more amplitude. This glass vibrates with more amplitude. Okay, then you may break that glass. It breaks at resonance because of more vibration, because of vibrations with more amplitude. So resonance means if the frequency of an object matches the frequency of the driving force, then resonance occurs. Here you can see induction heating. Okay, induction heater works on resonance. Okay, induction heating is heating conductive metals with no physical contact by using high frequency electricity. Here we use high frequency electricity in order to heat conductive metals. Okay, here we use the concept of resonance. Okay, guitar. Okay. Here a guitar produces sound entirely by vibration. Okay. In an acoustic guitar, when you pluck a string, okay, here you know, right? When you pluck a string, okay, When you pluck a string, it vibrates and transmits the sound energy into hollow wooden. Okay, here you're going to have guitar like this. Okay, you're going to have guitar like this. Right? Okay, is what hollow wooden guitar, right? So when you pluck a string, it vibrates. This string vibrates and transmits the sound energy into the hollow wooden body of the guitar. Okay, and making it resonant and amplifying the sound. Okay, means here you are going to have air column instead of this hollow body. Instead of this hollow body, you're going to have air column. Okay, so if frequency of the string matches the frequency of that air, okay, then resonance occurs. Then you're going to get more sound. Pendulum. Okay. The pendulum works on the same principle as the string. Okay, so we'll go for a string example also. Okay, so if we push the pendulum, okay, here give one push to this pendulum. Okay, if we push the pendulum, it moves back and forth. Okay, it moves back and forth. When you push the pendulum, it moves back and forth. Okay, continuous pushing at regular intervals of time will cause an increase in motion of the pendulum. Okay, so if you give regular pushes, if you give regular pushes or periodic pushes, okay, if your pushes are regular, okay, then you can increase the motion of this pendulum. I mean, if regular pushes are given to the pendulum, its motion can be built enormously. Okay, that is, you can increase the motion of this pendulum by giving regular pushes, by giving periodic pushes. Means that periodic pushes means those periodic pushes are having frequency. Okay, that frequency matches the frequency of pendulum. Then you can increase the motion of this pendulum with more amplitude. With more amplitude. If we give irregular pushes to this pendulum, you can't increase the motion of this pendulum. If we give regular pushes to this pendulum, then only you can increase the motion of the pendulum. Okay, that is the frequency of pushes has to match the frequency of an object. Then only motion of the pendulum will be increasing. That is resonance occurs. Going to swing example. Okay, swing. A playground swing is one of the familiar examples of resonance, right? Okay, when we push the swing, okay, here when we push the swing, it starts moving forward and backward. Okay, when you push the swing, it starts moving forward and backwards, right? If a series of regular pushes are given to the swing, if regular pushes are given to the swing, then you can increase the motion of the swing. You can increase the motion of the swing, right? Okay. If you give irregular pushes to the swing, you can't increase the motion of the swing. Okay. That is, the person who is pushing the string has to match the timing of the swing. Okay. The pusher has to synchronize with the timing of the swing. This causes the motion of the swing to have increased amplitude so as to reach higher. Okay. So in order to increase the motion of this swing, you are supposed to give regular pushes. Okay. Regular pushes must be given to the swing. Then only the swing motion of the swing will be increasing. Motion of the swing will be increasing. If you give irregular pushes, then you can't increase the motion of the swing. You can't increase amplitude of this swing. Okay. So that is, swing is an object. it is having its own frequency called natural frequency if periodic motion. See this periodic, here you are applying some force on swing. It is periodic force. Periodic force is applied to the swing. Okay, so frequency of that periodic force, frequency of that periodic pushes. Okay, periodic force or driving force. Okay, force matches the frequency of swing, then resonance occurs. Means at resonance, the motion of this swing will be more. Okay, it is this swing will be in motion with greater amplitude. Okay, you can increase the motion of the swing at resonance. Next, coming to this phenomenon of presence. Okay, Tacoma bridge collapse. Here, a group of soldiers on bridge. A group of soldiers while marching on the bridge. Okay, a group of soldiers while marching on the bridge. Okay, their rhythmic marching can set extreme vibrations at the bridge's nasal frequency. Means the frequency of marching. Okay, frequency of marching of a group of soldiers. Okay, group of soldiers are marching on this bridge. Okay, when they are marching means the frequency of marching of a group of soldiers matches the frequency of bridge, then resonance occurs. Okay, when soldiers are marching on the bridge, their rhythmic marching can set extreme vibrations at the bridge. Okay? If their synchronized footsteps resonate with the nasal frequency of the bridge, okay, then bridge gets collapsed. Okay, then bridge gets collapsed. Means frequency of marching matches the frequency of the bridge, then bridge gets collapsed. This incident happened in France. Microwave oven. The food is heated quickly in a microwave because of presence. Okay. The radiations emitted by microwave oven have a certain wavelength and frequency. Okay, so the radiations emitted by microwave oven. Okay, the radiations emitted by microwave oven have certain frequency, have certain wavelength and frequency. Okay, like all other objects, these radiations is having frequency. Okay, these radiations are having one particular frequency. Okay, so molecules of water and fat also have different frequency. Okay, at a certain frequency, the molecules absorb wavelengths and start vibrating. Okay, so if you place meat inside of this microwave oven, okay, then the molecules absorb wavelengths. Okay, those molecules of water, okay, absorb radiations. Okay. So this fat, this meat starts vibrating, okay, and causing cooking and heating up of food. Okay. So here, the frequency of that meat matches the frequency of radiations produced by microwave oven. Okay, so this microwave oven will produce radiations. Okay, radiations of heat, right? Okay, so if fat which is placed inside this microwave oven, okay, the frequency of this meat matches the frequency of radiations produced by microwave oven, then resonance occurs. Okay, so it represents, okay, this meat heats up. Okay, so the food is heated quickly in a microwave because of resonance. Okay. Next example is TV receivers. Okay, you're changing. See, you're going to have electromagnetic waves. Okay, you're changing. You're changing the channel means you're changing frequency. You're changing frequency. Okay, frequency of these electromagnetic waves matches the frequency of channel. Okay, then resonance occurs. Okay, frequency of this setup box. I mean, instead of this, we're going to have series RLC circuit or parallel RLC circuit. Okay, changing frequency means you are going to change the value of capacitance. You're going to change the value of capacitance. Okay, means you are going to change frequency. Okay, if this frequency matches the frequency of electromagnetic waves, then resonance occurs. Okay, coming to radio. So each station, each radio station emits electromagnetic waves. Each radio station emits electromagnetic waves of special frequency. Okay, each radio station has its own frequency. Okay, let it is 98.3. Okay, let it is 93.5. Okay, so in radio, we're going to have series RLC circuit. Okay, here changing this knob. Here changing this knob means you're wearing this knob means indirectly you're changing the value of capacitance. You're changing the value of capacitance. Okay, you're changing the value of capacitance. In turn, changing the frequency. Changing the frequency. Okay, if the frequency of RLC circuit matches the frequency of electromagnetic waves transmitted by one particular station, then resonance occurs. So that you can tune into one particular frequency. You can tune into a particular station. Okay, if frequency of electromagnetic waves matches the frequency of RLC circuit, then resonance occurs. Okay, resonance occurs means you can tune into a particular station. Okay, you can tune into this station. Okay, if both are matching, okay, then you can tune into this particular station. Okay, if the frequency of this station matches the frequency of RLC station, then you can tune into this station. You can tune into this station. Okay, so the frequency of electromagnetic waves of one particular station matches the frequency of RLC circuit, then resonance occurs. Okay, that is you're tuning into one particular station. Resonance. Resonance is the frequency response of a circuit or network when it is operating at its natural frequency, called resonance frequency. Okay, every object has its own frequency, own natural frequency. For many applications, the supply defined by its voltage and frequency, which is constant. Okay, so the supply to residential homes is 230 volts and 50 Hz. You not vary this frequency, you not vary this voltage. Okay, both are constant for home appliances. Okay, however, many communication systems involve circuits in which the supply voltage operates with varying frequency. Here the frequency is variable. Okay, in communication systems, frequency is variable. Okay, for home appliances, you apply fixed voltage and that voltage is operated at 50 Hz only. Will not vary voltage, will not vary frequency. Okay, whereas in communication systems, you vary frequency, right? To understand communication systems, one requires a knowledge of how circuits are affected by variation of frequency. Examples of such communication systems are radio. Okay, in radio you are changing frequency. Television also you are changing frequency. Telephones and machine control systems. Okay, in all these systems you will change frequency. In case of electrical circuit, how resonance occurs? Okay, when resonance occurs in any circuit that has energy storage element, at least one inductor, one capacitor. Under resonance, any circuit. Okay, for any circuit, under resonance, the total impedance is equal to the resistance only. Okay, the total impedance is equal to the resistance only. Okay, you are making imaginary part as 0. You are making reactance as 0. Means total impedance is equal to the resistance only. Okay, so that maximum power is drawn. Maximum power is drawn from the supply by the circuit. Okay. Under resonance, the total supply voltage and supply current are in phase. Okay, because the circuit becomes resistive in nature. Okay, you take a series RLC circuit, RLC circuit. You take series RLC circuit. Okay, this is XL is the reactance of inductor. XC is the reactance of the capacitor. Okay, R is the resistance of the resistor, right? Okay, so what is the total impedance? That is equal to R plus J into XL minus XC. XL minus XC. Okay, here what we do is we make both equal. XL is equal to XC. Means we make this imaginary part 0. Okay, if you make imaginary part 0, then Z will be equal to what? R. Okay, that's why under resonance, the total impedance is equal to the resistance only. The maximum power, so that maximum power is drawn from the supply by the circuit. Okay, under resonance, so see when Z is equal to R, okay, this circuit will be in resistive in nature. Right? Okay, so if it is resistive in nature, means only R is present here. Now R is at resonance, only R is present. Z is equal to R means only R is present. Okay, so these two are inactive. Means we take resistor. If V is the voltage applied across this resistor, okay, in resistive circuit, you take current as reference vector, then voltage will be in phase with current or not. Okay, in resistive network, in resistive circuit, okay, if the AC circuit containing only resistance, voltage is in phase with current. Means voltage, supply voltage and supply current are in phase. Both will be in phase. When both are in phase, phase angle is equal to 0 degrees. Phase angle is equal to 0 degrees. Okay. What is mean by phase? What is mean by phase angle? It is the angle between voltage and current. Okay. If phi is equal to 0 degrees means, see, when these two are in phase, when voltage and current are in phase, then phase angle must be equal to 0. When phase angle is equal to 0 means, what is the power factor of cos phi? Cos phi is equal to 1. Okay, so the point to be noted here is, at resonance, the circuit power factor is equal to unity. Okay, the circuit power factor is unity. And one more point is, the total impedance is equal to the resistance only. Even if it is parallel circuit only, even if it is parallel circuit, you make imaginary part 0 in the parallel circuit. Okay, then total impedance must be equal to resistance only. Okay, in series RLC circuit, total impedance is equal to resistance and the power factor is equal to 1. Okay, types of resonance. Okay, we have two types of resonance: series resonance and parallel resonance. Applications of resonance. Okay, resonant circuits are used in many applications, such as selecting the desired stations in radio and TV receivers. Okay, here you are changing frequency. Here we are changing frequency. Most common applications of resonance are based on the frequency dependent response. Okay, it is tuning into a particular frequency, a particular channel. Means you are changing frequency only. Okay, a series resonant circuit is used as voltage amplifier. A parallel resonant circuit is used as current amplifier. A resonant circuit is also used as filter. Next, coming to resonance in series RLC circuit. Resonance in series RLC circuit. Okay, so let us draw series RLC circuit. Okay, R L C. R XL XC. So what is the impedance? That is equal to R plus J into XL minus X. Okay. At resonance, XL is equal to XC. Okay. From this condition, you can find resonant frequency. Okay. So what is resonance? Sorry, resonance. Resonance. XL is equal to XC, right? So what is XL? XL is equal to omega L. That is 2 pi FL. Okay. As it is, it resonance 2 pi FR into L, which is equal to what is XC? 1 by omega C. Means 1 by 2 pi, as it is, it resonance FR into C. Okay, then what will be FR? FR is equal to 1 by 2 pi root LC. This is what? Resonant frequency. This is resonant frequency. Okay. In Hz. Okay. Then omega R is equal to, or omega naught is equal to 1 by root LC. 1 by root LC. Okay. Here 2 pi. 2 pi into FR is nothing but what? Omega. Okay, 2 pi f is nothing but omega. Okay, 2 pi into fr is nothing but omega r. So omega r is equal to 1 by root LC. This is also resonant frequency in radian per seconds. Radian per second. So here, what is the total impedance? Z is equal to R, and power factor cos phi is equal to 1, because phase angle is equal to 0 degrees, because voltage and current both are in phase. Voltage and current both are in phase. Okay. So here, let me do one thing. Let us draw resonance curve. Let us draw resonance curve. Okay. If omega is equal to 0, if omega is equal to 0, what will be Z? What will be impedance? Z will be infinity. See, here see, you know, right? Z is equal to R plus J into omega L minus 1 by omega C, right? Okay. So Z is equal to R plus J into omega L minus omega C. So if Z is equal to 0, okay, sorry, if Z is equal to 0, sorry, if omega is equal to 0, okay, if you put omega is equal to 0, omega is equal to 0, means 0 minus infinity, means Z will be infinity. So if omega is equal to 0, Z will become infinity. If Z is equal to infinity, means current will be 0 now. Current will be 0. Now, if omega is equal to infinity, if omega is equal to infinity, okay, what will be Z? Again, Z will be infinity. Again, Z will be infinity, because R plus J into infinity minus 0 means again Z will be infinity. Means again current will be 0. Current will be 0. Current will be 0. At resonance, okay, at resonance, at, at resonance, at resonance, Z is equal to R, means current is equal to V by R. Current is equal to V by R. If let V is the voltage applied across series RLC circuit. Okay, then I is equal to V by R. Okay, let me plot resonance curve. Okay, this is what? This is resonance curve. Resonance, resonance, resonance curve. Okay, okay, define this resonance curve. It is a graph between current versus frequency. If you plot the graph between current versus frequency, that will be the resonance curve. Okay, so at omega, see, omega is frequency. With respect to omega, you are plotting graph. Okay, so when omega is equal to 0, current is 0. Okay, if you increase frequency, you're going to have graph of current like this. Okay, current will be increasing. Okay, and reaches maximum value. Reaches maximum value at resonance at omega r. It reaches maximum value at omega r. Okay, at this resonance, current will be maximum value I max. Okay. Then after, current will be decreasing. Current will be decreasing. At omega t is equal to infinity. Again, current will be 0. But practically this is not infinity. This is larger value. If it is large value, means the frequency is more, means almost equal to 0, but it will not equal to 0. Okay, almost equal to 0 for higher frequencies. Okay, at higher frequencies, it will be current will be 0. So here see, this is series RLC circuit. Impedance of series RLC circuit R plus J into omega L minus 1 by omega C. Okay. Here net reactance becomes 0. Net reactance means omega L minus 1 by omega C is equal to 0. Okay. So here, if you make net reactance 0, means omega L is equal to 1 by omega C. Then FR is equal to 1 by 2 by root LC in Hs. Okay. Yeah. Here see. So what is the total reactance? X is equal to omega L minus 1 by omega C. This is the total reactance, right? Okay. So this depends on frequency. Again, coming to this inductive reactance, what is inductive reactance? XL is equal to omega L, which is equal to 2 pi FL, which is equal to 2 pi FL. Means with the increase in frequency, XL will be increasing. Means this reactance increases linearly with frequency. Okay, so you're going to have graph like this. Okay, XL increases linearly with respect to frequency because of this relationship. Because of XL is equal to 2 pi FL, with the increase in frequency, XL will be increasing linearly. Okay, coming to XC, XC is equal to 1 by omega C is equal to 1 by 2 pi FC. With the increase in frequency, capacitor reactance will be decreasing. With the decrease in frequency, capacitor reactance will be increasing. Means decreases, reactance decreases with the frequency. And it is largest at lower frequencies. Okay, that's why you're going to have graph like this. Okay, so with the increase in frequency, this capacitor reactance will be decreasing. This is decreasing, right? Okay. Here you can see this is where difference occurs, right? Okay, F less than FR, if F is less than FR, means for lower frequencies, for lower frequencies, frequency is less, low frequency, low frequency. Frequency is low means XC will be more, okay. For higher frequencies, XL will be more. So for lower frequencies, XC must be greater than XL. For higher frequencies, XL must be greater than XC. So here see, it is given at resistance Z is equal to R. Okay, below FR, XL is less than XC because low frequencies. For low frequencies, XL is less than XC. Okay, because XC, you know, right? XC is equal to 1 by omega C. 1 by omega C. Okay, so if frequency is low means XC will be more. Whereas XL is what? XL is equal to 2 pi FL. If frequency is low means XL will be low. Okay, so that's why below FR, below resonant frequency, okay, below resonant frequency, XC is greater than XL. Above resonant frequency, XL is greater than XC. Okay. So the circuit is more inductive and the power factor is lagging. Okay. You can draw resistance, reactance, impedance with respect to frequency. resistance. Okay, resistance versus frequency. Resistance versus frequency. Resistance is independent of frequency. So this will be, sorry, this will be, resistance will be constant. Resistance will be constant. Okay, so this will be what? This is R. Resistance doesn't change with respect to frequency, right? Coming to XL, XL is equal to what? 2 pi FL. Okay, with the increase in frequency, XL will be increasing linearly. So XL increases linearly. This is what? This is XL. Okay, coming to XC. Okay, XC decreases because here the XC is equal to what? XC is equal to 1 by 2 pi FC. With the increase in frequency, XC will be decreasing. Okay, inversely proportional to the frequency, right? So this is what? This is XC. Okay. I'm drawing this XC in this quadrant because of minus JXC. Okay, you can also draw in first quadrant. Okay, if you draw in first quadrant, you're going to get XC like this. XC decreases with respect to frequency. Okay. So this is XL, this is XC, right? Okay, so if you take magnitude, then this will be mod XL. Okay, let me take impedance of inductor. Then this will be JXL. This will be JXL. Okay, so this magnitude is JXL. Okay, this magnitude is equal to, is nothing but JXL. If we take impedance of this capacitor, then minus J XC. Okay, so here let this is plus JXL. Anyhow, this is plus JXL. Then this will be minus J. This magnitude would be minus JXC because it is XC with respect to frequency is XL with respect to frequency, right? Okay, so here this magnitude is equal to this magnitude. Both are equal now. JXL is equal to minus JXC. Okay, both are equal. When both are equal means what will be the total reactance? Total reactance will be equal to 0. Total reactance is equal to 0. J into XL minus XC is equal to 0. Okay, so let me draw. Means at this instant, reactance, total reactance is equal to 0. Means how can you draw impedance? When total reactance is 0 at this instant means how can I draw Z? Z is equal to R at this instant. At this instant, Z is equal to R. Okay, so so you're going to have Z like this. Z here. Okay. Now here, that is at resonance. Okay, at resonance, Z is equal to R. At resonance, total reactance must be equal to 0. Okay, and Z is equal to R. Z is equal to R. Then how can I draw? Z is equal to R. Okay. When F is less than FR, we're going to have impedance like this. When F is greater than FR, you're going to have impedance like this. This is impedance curve. Impedance curve. See, this is mod z curve. You know, right? Z is equal to what? Z is equal to R plus J into XL minus XC. XL minus XC. Then here, this portion is F less than FR. Okay, this portion is F greater than FR. Okay, for F less than FR, XC is greater than XL. You can see here. You can see here. X is having this much magnitude. XL is having this much magnitude. Okay, so XC is greater than XL. Okay, here F is greater than F greater than FR. Okay, XL is greater than XC. XL is greater than XC. Okay, so here when F is greater than FR, XL is greater than XC. XL is greater than XC. Okay, so in both cases, any one of reactance is more. Any one of reactance is more. Means what will be the impedance? That is equal to magnitude of impedance. That is equal to under root of R square plus XL minus XC. XC whole square. XC whole square. Okay, so for F less than FR, for F greater than FR, any one of reactants is more. Means Z will be more only. Z will be more. Okay, so starting Z will be more. Okay, when it is approaching resonance condition, then Z will be decreasing and equal to R. Okay, then after Z will be increasing. Okay, so this is impedance curve. Okay, this is XL minus XC. XL minus XC is equal to 0 at this point. When it is 0 means impedance is equal to R. Okay. So yes. Below FR, XL less than XC. Phi is negative. See here. Below FR means F less than FR. F less than FR. XC is greater than XL. This is important. Okay, then you're going to have phasor diagram like this. Okay, you can draw the phasor diagram, right? Okay, RS circuit. Okay, take I as reference vector. Okay, then this will be VL. VL leads I by an angle 90 degrees. VC lags I by an angle 90 degrees. Right? So here XL is greater than XL means VC is greater than VL. Okay, then we can have this. Okay, where is sum of these two? Okay, VR. Okay, VR. Okay, let this is VC. Then this will be VC minus VL. Okay, where sum of these two gives what? Total voltage. Okay, so from this VR is equal to IR. VR is equal to IR. Okay, VL minus VC is equal to I into XL minus XC. Okay, so the phi will be negative. Okay, it represents XL is equal to XC. So Z is equal to R only. Okay, so you're going to have lagging power factor here in this case. Okay, phi is positive. Okay, it represents XL is equal to XC. It represents XL is equal to XC. Phi is equal to 0 degrees. Then Z is equal to R. Then what will be current? Current will be maximum, that is equal to V by R only, because Z is equal to R. We're going to have resonance curve like this. Okay, Im is equal to V by R. At resonance, okay, already we have discussed about this, right? Resonance curve. Okay, at omega is equal to 0, at F is equal to 0, current will be 0. With the increase in frequency, current will be decreasing, and almost it is equal to 0. Okay, it is having low value. Okay, current will be less. Okay, it resonance. Here, this is what is F less than Fr. F less than Fr. Okay. Okay, this portion is F greater than Fr. Okay, this instant is F is equal to Fr. At resonance, Z is equal to R and Im is equal to V by R. Okay, so at resonance, net reactance is 0. Net reactance is 0. Okay, below resonant frequency, XC is greater than XL. Okay, above resonance frequency, XL is greater than XC. So coming to quality factor, this indicates sharpness of the resonance curve. Okay, see, the curve is sharper. Okay, let me draw the curve like this. Okay, if you have curve like this is having low quality factor. If you have curve like this is having more quality factor. If you have sharp resonance curve like this is having more quality factor when compared to this curve. This is having more quality factor than when compared to this curve. Okay, that indicates resonance quality factor indicates sharpness of the curve. Okay, the sharpness of the resonance in a resonance circuit is measured qualitatively by the quality factor. Okay, the quality factor relates the maximum of peak energy stored to the energy dissipated in the circuit per cycle of oscillation. Okay, we have formula. Okay, 2 pi into peak energy stored in the circuit by energy dissipated by the circuit in one period at resonance. Okay, so applying that formula, we're going to have this 2 pi Fr L by R. See, another way of defining this Q, okay, simply Q is equal to, okay, it is defined like this. It is the ratio of voltage across inductor or capacitor to the applied voltage. Okay, another way of defining Q factor. Okay, Q is equal to, it is the ratio of voltage across inductor or voltage across capacitor. It is ratio of voltage across capacitor or inductor to voltage across it is ratio of voltage across inductor or capacitor to the applied voltage. To the applied voltage at resonance. To the applied voltage at resonance. Okay, so here now VL by what is the applied voltage at resonance? VR only, because XL is equal to XC at resonance. When XL is equal to XC at resonance means what will be applied voltage? Applied voltage is equal to, normally applied voltage V is equal to VR plus J into VL minus VC. VL minus VC, right? Okay, when XL is equal to XC means VL is equal to VC. Then this part becomes 0. Then V is equal to VR. Then applied voltage becomes VR. Then Q is equal to VL by VR. It represents this VL is equal to what? I into XL. I into XL by I into R. It represents which is equal to, what is XL? XL is equal to omega R L. It represents by R. Okay, which is equal to 2 pi Fr, 2 pi Fr L by R. Okay, so you're getting the same formula. Right? Okay, simply omega R L by R. Okay, or omega naught L by R. Okay, 2 factor 2. Okay, so you know, right? Fr is equal to what? Fr is equal to 1 by 2 pi, 1 by 2 pi root LC. 1 by 2 pi root LC is Fr, right? Okay, we put this in this equation, then you are going to get Q is equal to 1 by R root L by C. Another way of defining Q factor. Q factor Q is equal to reactive power by average power, which is equal to I square XL by I square R, which is equal to omega RL by R. Okay. So in Resonance circuit, coming to voltage, phasor diagrams for voltage. Okay. See, VR is in phase with I. Okay. Here for F is less than FR means XC is greater than XL. Okay, so VC is greater than VL. Okay, then you're going to have phasor diagram like this. Okay, here Z is equal to R. Okay, VL is equal to VC. When VL is equal to VC means V is equal to VR only. That's why here V is equal to VR. Okay, here XL is greater than XC means VL is greater than VC. Okay, then you're going to have VL minus VC phasor like this. Okay, where sum of these two gives V. Okay. So the circuit is inductive. I lack C. Here the circuit is capacitive. I is V. Voltage across RLC circuit, RLC element at resonance. Okay. So what is the voltage across resistor at resonance? VR is equal to IR into R. IR is nothing but IM only. IM is equal to V by R. V by R into R. Then VR is equal to V. Okay, because it represents XL is equal to XC. VL is equal to VC. Then applied voltage V becomes VR. Coming to voltage across inductor. VL is equal to XL into IL, omega RL into IM, omega RL into V by R. Okay, finally you are going to get QV. Okay, so VL is equal to QV. Okay, again here VC is equal to QV. Okay, both will be equal. Both will be equal at resonance. Both are equal at resonance. Okay, VL is equal to VC at resonance. Okay, so VL is equal to Q times V. VC is equal to Q times V. Means this series RLC circuit magnifies voltage. Okay. Voltage magnification. That's why it is called voltage magnification. Okay, you know this, right? And here, in a series RLC circuit, at resonance, maximum power is what? Okay, only resistance Z is equal to R at resonance, right? Z is equal to R. Okay, only resistance is present, right? So what will be current? Current I max is equal to V by R only. Okay, I max is equal to V by R. What will be power? Power is I max square into R. Here we have this omega 1 is called lower half frequency. Okay, omega 2 is called upper half frequency. So this omega 1 is called lower cutoff frequency, whereas omega 2 is called upper cutoff frequency. Okay, these two are half power frequencies, half power frequencies. Okay, fine. Now the difference between these two frequencies is called bandwidth. So the bandwidth is equal to what? Bandwidth is equal to omega 2 minus omega 1. Omega 2 minus omega 1 or f2 minus f1 in terms of frequency. F2 minus f1 is called bandwidth. Bandwidth. Bandwidth in radians per second is W2 minus W1. Bandwidth in Hz is equal to F2 minus F1. Okay, the difference between these two, upper cutoff frequency and lower cutoff frequency. Okay, this is upper cutoff frequency, whereas this is lower cutoff frequency. The difference between these two frequencies is called bandwidth. Is called bandwidth. Okay, so lower cutoff frequency or upper cutoff frequency. Okay, this occurs at half power, half of the maximum power. Okay, so here it is written. Bandwidth represents the range of frequency for which the power level in the signal is at least half of the maximum power. Half of the maximum power. It is half of the maximum power. Okay, right? So here see, it represents power is maximum, that is equal to I max square into R. At lower cutoff frequency or upper cutoff frequency, power will be half of the maximum power. So PR by 2 is equal to I max square into R by 2, which is equal to I max by root 2 whole square into R. Means what will be the current? Here the current is I max, means here the current will be I max by root 2. Okay, so at lower cutoff frequency or upper cutoff frequency, the current is I max by root 2. Okay, so at lower cutoff frequency, the current is I max by root 2. At upper cutoff frequency, the current is Im by root 2. Okay, Im by root 2. Here also Im by root 2, right? Okay, so what is the bandwidth now? Bandwidth is the difference between two frequencies, upper cutoff frequency and lower cutoff frequency, right? Okay, so now how can you define bandwidth? Okay, here we can define the bandwidth like this. It is the range of frequencies over which, okay, it is the range of frequencies over which current is equal to or greater than 70.7% of maximum current. Okay, so here see, this is nothing but what? This is equal to 0.707 I max. 0.707 I max means it is the range of frequencies. Bandwidth, you can define the bandwidth like this. It is the range of frequencies over which circuit current is equal to or greater than 70.7% of maximum current. Okay, 70.7% of maximum current. Okay. So at lower cutoff frequency or upper cutoff frequency, the current is equal to what? I max by root 2. Okay. At lower cutoff frequency or upper cutoff frequency, the impedance is equal to, see here, what is the current at lower frequency, lower cutoff frequency or upper cutoff frequency? Im by root 2, which is nothing but V by R root 2. This will be the impedance at lower cutoff frequency or higher cutoff frequency. So let me make the half power frequencies are obtained, means lower cutoff frequency and upper cutoff frequency. Okay, both can be obtained. Okay, by making impedance is equal to root 2 R. This is the impedance at lower cutoff frequency as well as upper cutoff frequency. So I am making this impedance equal to root 2 R. Okay, then after solving this, you are going to get omega 1 is equal to lower cutoff frequency, omega 1 is equal to minus R by 2L plus under root R by 2L square plus 1 by LC. Okay, upper cutoff frequency is this thing. R by 12 plus under root of R by 12 whole square plus LC. Here see, you know right, what is Q? Q is equal to, given right, 1 by R root LC, right? So 1 by R root L by C. So by using this equation and this equation, these two equations, we are going to get W1 and W2 in terms of Q factor. Okay. You know bandwidth is equal to W2 minus W1, which is equal to WR by Q. Okay. From this, see, by using these two equations, okay, W2 minus W1 is equal to WR by Q. Okay, you remember, it is better to remember this formula. Bandwidth is equal to, the bandwidth is equal to W2 minus W1. Okay, which is equal to resonant frequency by Q factor. Okay, solving this is somewhat difficult. Not that much difficult. Okay, you need to spend time to solve this. So instead of spending time to solve that, it is better to remember only this formula. Okay, just you remember anyhow. Bandwidth is equal to W2 minus W1. All you need to remember is bandwidth is equal to omega R by Q, resonant frequency by Q. Okay, bandwidth is equal to resonant frequency by Q. Okay, this is geometry. WR is equal to under root omega 1 into omega 2. If Q is greater than, far greater than 1, or if Q is greater than 10, if Q is greater than 10, okay, this resonant frequency is located centrally. This is located centrally. Okay. So if it is located centrally, means what will be FR? FR is equal to F1 plus F2 by 2. Right? Okay, otherwise omega R is equal to omega 1 plus omega 2 by 2. Okay. So here see, what is bandwidth?
Sir, you are not audible. Mute అయ్యి ఉన్నారు సార్ మీరు.
It's okay, I think.
Yes, sir.
Here see. Okay, bandwidth is equal to W2 minus W1 is equal to omega r by Q. Okay, so here see, if Fr is located centrally, if omega r is located centrally, then F1 plus F2 by 2. Okay, Fr is equal to F1 plus F2 by 2. Okay, then from this F1 plus F2 is equal to 2Fr. Okay, so if omega r is located centrally, then Fr is equal to, or omega r is equal to omega 1 plus omega 2 by 2. Okay, from that F1 plus F2 is equal to Fr. Okay, so F1 plus F2 is equal to Fr. Okay, you know bandwidth is equal to F2 minus F1 is equal to bandwidth, Okay, in terms of angular frequencies, W2 minus W1 is equal to bandwidth, W1 plus W2 is equal to Fr, or 2 omega. Okay, so after solving these two equations, okay, these two will get cancelled each other. Okay, then F2 is equal to Fr plus bandwidth by 2. Okay. So omega 2 is equal to, or F2 is equal to omega r plus bandwidth by 2. Similarly, okay, you can get F1 from these two equations. Okay, then omega 1 is equal to, okay, omega r minus bandwidth by 2. Here see, if R is equal to 2000 ohms, so let me have let us have L is equal to some 0.5 Henry. Okay, C is equal to some we take 0.1 microfarad. Okay, if R is equal to 2000, okay, you're going to have curve like this. Okay, here Q1 is for R is equal to 2000. Q2 is for R is equal to some, you take 600, some resistance 600 ohms. You take R is equal to 200 resistance, 200 ohm resistance. Okay, so you're going to have curves like this for different values of resistances. Okay, for R is equal to 2000, you're going to have curve Q1. Okay, this is the curve you're going to get. Okay, for R is equal to 600 ohms, you're going to have curve like this. This is the curve for R is equal to 600 ohms. This is the curve for R is equal to 200 ohms, you're going to have curve like this. Okay, so you're going to have curve like this for R is equal to 2000. You're going to have curve like this for R is equal to 600 ohms. You're going to have curve like this for R is equal to 200 ohms. 200 ohms. Okay, coming to the observation. Okay, for R is equal to 2000 ohms, we're going to have more bandwidth. Bandwidth is more. Okay, bandwidth is more for R is equal to 2000. Okay, let this is B1. Okay, this is the bandwidth. Bandwidth is more. Bandwidth is more. For R is equal to 600 ohms. Okay, bandwidth is less. Okay, this will be B2. Bandwidth is less. For R is equal to 200 ohms, we're going to have curve like this. Bandwidth is narrow. Narrow bandwidth. We're going to get bandwidth is narrow. Okay, B3. Okay, here B3 is less than B2 less than B1. Okay, so here bandwidth is more bandwidth. It is more bandwidth. Okay, here bandwidth is less bandwidth. Okay, less bandwidth means more selectivity. More bandwidth means less selectivity. Okay, if bandwidth is more means less selectivity. Selectivity is less selectivity. Okay, if bandwidth is less means more selectivity. Okay, if bandwidth is more means less selectivity and less Q factor. If bandwidth is less means more selectivity and more Q factor, more quality factor, because Q indicates the sharpness of the curve. Here we are having more sharpness of the curve. In case of R is equal to 200 ohms. Okay, if bandwidth is less, means more selectivity and more Q, because sharpness of the curve is more. Okay, so why Q is more, why selectivity is more? Let us take radio example. Okay, so here see, if R is equal to 2000, you're going to have curve like this. If R is equal to 600, you're going to have curve this curve. You're going to have this curve. You're going to have this curve when R is equal to 200 ohms. When R is equal to, okay, when R is equal to 2000 ohms, you're going to have curve like this. When R is equal to 600 ohms, you're going to have curve like this. When R is equal to 200 ohms, you're going to have curve like this. Okay, here the curve is sharper than other curves, right? Okay, if R is less, means Q will be more. Okay, so here see, let us come to this curve. For R is equal to 2000 ohms. For R is equal to 2000 ohms, bandwidth is from here to here. Means B1 is bandwidth from here to here. Bandwidth is more. Okay. See, let resonance occur at this instant. Okay. Resonance occurs at this instant. Okay. So if you move away from this resonance frequency, okay, this current curve doesn't doesn't fall sharply. Okay, it is almost constant. Current is almost constant. It is not changing rapidly. Okay, so that's why it is having less selectivity. selectivity will be less. Okay, so coming to this curve, okay, if we move away from this resonant frequency, the current drops sharply. Okay, the current falls off sharply if we move away from this resonant frequency. Means reception get more clarity. Reception get more clarity. Then you can tune into one particular frequency easily. Okay, you can tune into one particular station easily, because if you move away from this resonant frequency, okay, clarity will be missing, because current falls off sharply. Current falls off sharply means you can miss the clarity easily. Okay, at resonance you are going to have more clarity. You are going to have more clarity. Station will be very clear at resonance. Okay, if you move away from this resonant frequency, okay, usually you can recognize the clarity of the station. Okay, because current falls off sharply. Coming to this curve, current doesn't fall sharply. Okay, current is not changing rapidly. It is almost constant. There is small change in current if you move away from this resonant frequency. Means the clarity will not be. You will not get clarity. Okay, station will not be clear. Station will not be clear if you move away from this resonant frequency. Okay, that's why Q will be less. Selectivity is less. For this curve, if bandwidth is less, more selectivity, more Q, for having less resistance. For having more resistance, less Q factor, bandwidth will be more, selectivity will be less. This relationship is important. So bandwidth is more means Q factor will be less. Selectivity will be less. Less selectivity means because of what? High resistance. Okay, coming to conclusions. Right? As VL is equal to Q into V, VC is equal to Q into V, it represents, okay, series RS circuit magnifies voltage. Okay. Let us go for 3 problems. So first problem, the circuit below, R is equal to 2 ohms, L is equal to 1 millihenry, C is equal to 0.4 microfarad. Find the resonant frequency. Next, calculate the quality factor and bandwidth. Next, determine the amplitude. Determine the amplitude maximum value of the current at omega r, omega 1 and omega 2. Okay, so it represents, it represents omega is equal 1 by root LC. Okay, 1 by root, you set to the values of LNC, you are going to get 50 kilo radian per second. Okay, you know the formulas for lower cutoff frequency and upper cutoff frequency. Omega 1 is equal to 1 by minus r by 12. This formula, right? Okay, substitute all values in this formula, you're going to get 49 kilo radian per second. Okay, if you substitute all formulas in this values in this formula, then you're going to get omega 2. This is lower cutoff frequency, this is upper cutoff frequency. Okay, what is the bandwidth? Bandwidth is equal to 2 kilo radian per second. That is the bandwidth. Okay, so here another way of solving, okay, this bandwidth and W1 and W2, okay, you can solve like this. You know this formula, right? Okay. See, first of all, you find omega naught or omega r. Okay, after that, you know this formula, bandwidth is equal to omega r by q. Omega r by q. Okay, you know how to find q. Q is equal to, you find omega r and then you find q. Q is equal to 1 by r root L by c. Root L by c. 1 by r root L by C. Okay. Q is equal to 1 by r root L by C, or otherwise you can also use this formula. Okay, Q is equal to omega r L by r. Okay, you can use this formula. Okay, so first you find resonant frequency, then after you find Q, then you can find bandwidth. You can find bandwidth. Okay, so here bandwidth is equal to what? Bandwidth, after finding bandwidth, you know bandwidth is equal to W2 minus W1. Okay, if resonant frequency is located centrally, anyhow, here, I mean, Q must be greater than 10. Okay, here you will get Q is equal to 25. Q is equal to 25. Okay, so Q is equal to 25 means Q is greater than 10. If Q is greater than 10 means resonant frequency is located centrally. If resonant frequency is located centrally means we have formulas, right? W1 is equal to what? W1 is equal to omega r minus bandwidth by 2. Minus bandwidth by 2. Okay, next omega 2 is equal to omega r plus bandwidth by 2. Bandwidth by 2. Okay, substituting all values omega r and bandwidth, you are going to get lower cutoff frequency and upper cutoff frequency. This is an alternative way of solving this problem. Okay. Next, here after finding omega 1 and omega 2, here see one way of finding is first you find omega r, then after omega 1, then omega 2, then you find bandwidth W2 minus W1, then you find Q. Okay, and another way of solving this problem is first you find omega r, then you find Q, then you find bandwidth, then you find lower cutoff frequency and upper cutoff frequency. Okay, then coming to this amplitude of current at resonance. Okay, I is equal to Vm by R, maximum value is equal to 20, 20 by 2 is equal to 10 amps. Okay, at omega is equal to omega 1, from omega 2, you know, right, at upper cutoff frequency and lower cutoff frequency, at omega 1 and omega 2, okay, I is equal to Vm by root 2R. Already we have discussed. Okay, power becomes half, maximum power becomes half, and Vm by root 2R is equal to I. Then you are going to get this value. Okay, a circuit having a resistance of 4 ohms with an inductance of 0.5 Henry and a variable capacitance in series is connected across a 100 volts. Just calculate the capacitance required to attain resonance. Voltage across inductance and capacitance at resonance, the quality factor of the circuit. Okay, so at resonance, you know, XL is equal to XC. So from this you can find the value of capacitance. You can find the value of capacitance. Okay, at resonance, I is equal to V by R. Simply V by R. Okay, 100 by 4 is equal to 25 amps. Okay, voltage across resonance, VL is equal to omega R into L into I. XL into I, right? XL into I. XL is equal to what? Omega R into L at resonance. So 2 pi, you know, this XL, right? Okay, 2 pi FL. Okay, resonant frequency is given, right? Yeah. Okay, frequency is given. Okay, so F is equal to 50 Hz. F is equal to 50 Hz. Okay. See, a circuit having a resistance 4 ohms with an inductance, okay, variable capacitance in series. It is connected across this. Okay, the capacitance required to attain resonance. Okay, so we can use this frequency. Frequency is given. Okay, from this we can have capacitance. Okay, after this 2 pi FL into R. Sorry, 2 pi FL into I. You're going to get this values. Okay, VC is equal to 1 I into XC. Okay, I is 25 by omega C. Omega is 2 pi F FC. Okay, you're going to get this. We know Q is equal to XL by R or omega L by R. Okay, omega is equal to what? 2 pi FL. The last column. The bandwidth of series resonant circuit is 500 Hz. If the resonant frequency is 6000 Hz, what is the Q factor? If R is equal to 10 ohms, what is the value of inductive reactance at resonance? Calculate the inductance and capacitance. Okay, you know bandwidth is equal to resonant frequency by Q factor. Q is equal to FR by bandwidth. Okay, then you can find Q is equal to 12. Okay, Q is equal to XL by R. XL is equal to Q into R. Then you can find XL, the value of XL. XL is equal to 2 pi FR into L. Okay, from this you can find L. Okay, it represents XL is equal to XC, which is equal to 120 ohms. Okay, from that you can find the value of